So let's start with some fundamental concepts of graphs at just the generic level of, this is a graph. Forget the data, forget the problem. We talked about that in the last bit of video for a little bit, the types of things we can solve. Right now, we just want to talk about the raw mechanics of graphs. So a very simple depiction of a graph includes the little circles and the lines here. The circles are vertices, or each circle known as a vertex, and that is just some representation of some point. You could view these as different family members and the relationships between them. People right there. These could be different streets. There could be different corners in a maze. They could be different movies. Whatever type of data you want. It doesn't matter. It's just the saying that we have these individual elements, and then there's some defined connection between them. So, it could be movies, and the connection between them is common actors, or common special effects teams, or storylines, or something like that. So again, this is the drawing representation, and it's important to be able to picture this to some degree because it will help you understand what the algorithms are doing. So the important thing is that each of these vertices is a set. In general, we don't want copies of things into a graph because it just becomes confusing because then we have multiple things to accommodate. So, for the most part, we want to create graphs that are sets of of vertices and then a collection of edges. So it could also be a set of edges to some degree, but typically we start off with the idea of there could be duplicates of edges, which gets us into some of this anomalous relationships, the idea of a multigraph. And so, for instance, in this instance, we have two vertices, C and E, excuse me, which could share multiple edges. There could be three common relationships between these two things. So again, the idea of having two movies, maybe there's three actors that were in two movies, or three crew members that were each in two movies, or three other movie references, or whatever you might be tracking between there. And then there's also the idea that a vertex could have an edge to itself. Again, this it's kind of a weird notion, depending on what the data type is. But again, we could be talking about um, employer-employee relationships. And so maybe at one point, C worked for E at three different companies, and in some strange twist of the world, E was also a boss to themselves because, uh, they were the CEO and the president of a company. So the CEO, the president reports to the CEO, and so they reported themselves in some weird way, or something like that. Again, that's just one example. We're not necessarily worried about the examples here. The examples come in the context of the problem you're trying to solve. But in some cases, graphs are allowed to do this. In other cases, not. There's no logical, I mean, if there's a relationship between two people, I don't need to characterize that three different ways in some applications. I don't need to be somebody's boss and mother and friend. They could be simply just the two people are related in different in different graphs. But again, we're just talking about the mechanics. So it's possible. It's also possible to avoid those things. So let's talk some of the terms in graphs here. So the first thing we can talk about is when we have two vertices, so A and B, for instance, that are connected by an edge, or in this case, D and F, they are adjacent to each other, and each of these D and E are incident to the edge. So the term incident probably isn't going to be used as often, but basically two vertices that have a edge between them are become adjacent. If they don't, they're not. And it's an important concept because the physical location of things, as they're depicted here, don't really mean anything. The physicality of how we would draw something is out of convenience, out of a choice. But we could have a million nodes that are adjacent to each other, and you'd never be able to draw all of them being close to each other. You might have to layer them or have them be separated by a long way, like the visualization we saw in the last video. But they're still adjacent as long as they have an edge between them. Um, the other concept we can talk about here is the idea of a subgraph, which is some smaller set In this case, you can see a few of these lines have turned purple inside of here. And so A, C, E, and F are also a graph that happen to be a subgraph of this larger graph that also includes D, G, and B. And so a sequence then is some connection, in this case A to C to E to F, of of connections of adjacent of nodes. So A is in this case adjacent to both C and E, but A being adjacent to C, being adjacent to E, being adjacent to F forms a sequence. And so sequences are important because they help us define paths. A path is basically some connection of one vertex to another vertex up to from one point to another. So in this case, we have a simple path of four, A, B, G, A, B, G, F, E. So there's five vertices involved, but four edges. So the path size is four. We can also have a cycle, which is a path that starts and ends at the same vertex. So in this case, A, B, G, F, E, A is a cycle of length five, so five edges between. The same cycle as B, G, F, E, A, B. Doesn't matter where it starts and ends per se, but the point is it goes all the way around in whichever direction or lack of direction it's going to go. So again, the path that can be identified by essentially, the writing that you might see in different books or in different resources is basically naming each of the vertices in a row. So A, B, G, F, E, A, starting with one, ending at the same one. It shows the name, quote unquote, of that path in case you are seeing something written down. So another notion, since there's paths involved here, is if there's a path to every vertex in a graph, it's what's known as a connected graph. It's not always going to be the case that graphs are entirely connected. If you talk about roadways, the you know every city in the United States is not connected to every other city in the United States because of Hawaii. Hawaii is an island out there. Every city in the continental United States is connected to every other city through roads. I don't know that there's probably, I mean, it could be a dirt road or something pretty remote, but there's still some connected graph inside of there. But it doesn't mean that every road in the world is connected to every other road in the world. So if I toss in any vertex that's not connected to everything else, now the graph is no longer connected. So very, very simple concept, but it's important as we talk about searching later on that we need to see, are the two things in the graph connected for any variety of questions we might want to ask. So there is at some level a conceptual and practical relationship between graphs and trees. So we have this graph here. But if we consider a subgraph of the main graph, where let's say we just ignore certain connections. So in this case, we're taking out the edge or ignoring the edge between C and E and between F and G. Well, then we remove any cycles. And so our graph becomes what's called acyclic. And then it becomes essentially a tree. Now, it doesn't necessarily have to be a sorted tree, and not every tree becomes a graph, and not every graph becomes a tree instantly. That's not, there's some commonality, but it doesn't necessarily have to be the case. But there can be certain relationships between these, and not only in graph theory and the mathematical side of it, but in the programming side of it, there could be reasons to create these intersecting structures. And so in this case, since the graph remains connected, it becomes what's called a spanning tree. It spans the entire graph. The tree has no unconnected elements within this graph. So we're not really going to explore this notion terribly much, but it's worth mentioning. So at least you understand that this isn't a completely unrelated thing to trees. And when you come across in the future, whatever classes you take in the future, if you come across this, you'll know that there is some relationship between graphs and trees. So I think the last thing we're going to talk about here is the notion of density. Not last thing total, but last thing in this video. Um, a graph's density is a relationship between how many possible edges there could be and how many edges are actually filled. So if you have theoretically a single edge between any two vertices, if you have two vertices, you typically have one edge. If you have three, vertices, then you could have three edges in between there. Again, if you don't duplicate any. So if you have three vertices and only one edge is filled, only your density is basically 1 out of 3. So you can see the difference between these two graphs of theoretically the same nodes, the same vertices, excuse me. Um, one has a whole lot, the one on the right has a whole lot of those connections in play. The one on the left doesn't have very many connections in play. I mean, there's things that are completely unconnected and the graph moves around, but the other one is very, very dense. There's a lot of connections here. And so, again, this has something to do with the algorithms and the way you work them, and basically how much processing is required to truly query and understand some of these graphs. So that's what's going to come up as we and you, even beyond this course, get into some of the theories of graphs if you continue to do that. So again, we're kind of just building the foundation of the terminology and the concepts. We are going to get into some of the coding aspects, but the coding aspects in some ways are way easier than the concepts of graphs. So starting to imbibe and play with these concepts will help you understand the code a little bit, but more importantly, will help you understand the application and use of graphs as we move forward and deal with other topics in them.